Hello everybody, welcome to section 7.3, and we're going to talk about solubility. Solubility is, as you'll see, basically the how well something will dissolve. That is, like if you've ever made tea, sweet tea, and you heat it up. If you put the sugar in there while it's hot, the hotter temperature will allow you to put more of the sugar and dissolve it in the tea water. If you get unsweet tea and you try to put sugar in it, sometimes it's very difficult to do, and so there's only a certain solubility of the sugar in the tea. So basically there are things that affect solubility, but basic solubility is how much is the maximum you can get to dissolve. Now if you put salt in water, you can get quite a bit of salt to dissolve in water, even if it's not hot. And because salt, table salt, has a higher solubility in water than does the sugar. And if you recall from the last section, the reason is because table salt is what? It's an ionic compound, so ionic compounds are going to dissolve much better typically in water than those molecular compounds such as sugar. Okay, so solubility is the maximum amount of solute that will dissolve in a specific amount of solvent. And usually, you know, you're going to talk about grams of water or liters or something like that. They are temperature sensitive, like I said, so the hotter, usually the more you can dissolve in there. And so you'll see it grams of solute per 100 grams of water. Okay, and water in this case is the solvent. So solute in solvent gives you the solution. An unsaturated solution basically means that it has less than the maximum amount. Alright, so you've put some salt in this water and stirred it up and you can't see it. Okay, so if you have, you can put some more in there and stir it again and you still can't see it. So you have not reached the saturation point or the maximum amount of solute that you can put in there. And that means that you can still dissolve more of whatever that solute is in that solution. A saturated solution, however, is when you have put so much in there that you begin to see some left over in the bottom. When you've done that, you've got this extra down here, then the solution that's here is saturated. Okay? And really the only way to know you have a saturated solution is if you've got some in the bottom. And that doesn't mean you shake it up and use that as a saturated solution. You know that once this settles, whatever this is up here is the saturated. So you have some undissolved solute at the bottom of the container, and so you know you're going to be still getting some back and forth from this residual here. Okay, so the solute plus the solvent is going to give you a saturated solution, and then you're going to be dissolving and then recrystallizing. So it's an equilibrium, we call it. It's going back and forth. So which of these would be saturated or unsaturated? Salt disappears when put in water. Is that saturated or unsaturated? How do we know it's saturated? Because we'll be able to see something. So this is not saturated. Sugar added to a cup of water does not disappear but sits at the bottom of the cup. That would be what? Saturated. At 40 degrees, the solubility of potassium bromide is 80 grams per 100 grams of water. Identify the following solutions as either saturated or unsaturated and tell why. Okay, you've got 60 grams of potassium bromide in 100 grams of water at 40 degrees C. The solubility is 80. So is it got as much as it can possibly take? No, it's not. So it's un. you've got 200 grams of potassium bromide in 200 grams of water. That's the same as what? 100 grams in 100 grams, right? Because 200 divided by 200 is the same thing as 100 divided by 100. I'm doing the 100 grams because that's what my solubility is talking about. So is this more than 80? Yes, so that would be saturated. 25 grams of KBr in 50 grams of water. Let's see, we got 25 grams of KBr in 50. We need that to be in 100 grams so we can compare it to the solubility. What did I have to do to 50 to get to 100? Multiplied it by 2. So that means I've really got 50 grams of KBr in 100 grams, and that's less than the 80, so it would be un. See how that works? So solubility can depend on several different things, but one of the major things that it depends on is temperature. This is the theme for the lab you're doing over this chapter. So lab 7 is about how solubility can depend on temperature. For most compounds that we see in general chemistry, if you increase the temperature, you're going to increase the solubility. In gases, the solubility decreases as you increase the temperature. So if you're in water, if you increase the heat, you increase the solubility, okay? In gas, if you increase the heat, you decrease the solubility. Okay, so that's the relationship. And what they're showing you here is that how these are solubility curves, because it's not like a straight line relationship. So in sodium chloride, if you have it at 20 degrees, okay, you can put about 30 grams in 100 grams. But if you crank that temperature up to 60 degrees, then you can actually dissolve 110 grams in 100 grams of water. Okay, so that's quite a bit. So why could a bottle of carbonated drink possibly burst if you leave it out in the hot sun? If it's in the sun, what are we doing? We're increasing the heat. And if we decrease the solubility of the gas, then, and inside that can, it's pressurized, right? But it has a little bit of head space here, and this is the liquid, and then this part is air space. And so you've heated it up, and it's pushing those gas molecules out of solution. Eventually, they may have enough force to explode that. Why do fish die in water that is too warm? This is a great question. Think about this for a minute and see if you can come up with something. Okay. What do fish need that they get out of water? Well, food, of course, and all that, but here's your water. You know, I'm not a very good artist, right? Okay, so we got our fish, okay, and fish have gills, and they need oxygen. And if the water gets warm, the oxygen will tend to leave the solution, and so there's less oxygen in the water, and you can have fish kills if that happens. And so some chemicals and runoff and things like that can also do that and have fish kills, because the fish have to get, unless they are the type of fish that come up and breathe air, the ones that get their oxygen from the water, if this oxygen gets too low, then they can't live, because they're not going to be able to pull enough oxygen out. Henry's law was a gas law, Okay? And what Henry's law states, this is the one about the bursting cans, is what I always think of it as. Henry's law says that the solubility of the gas in a liquid is related to the pressure of that gas above the liquid. At higher pressures, more gas molecules are going to dissolve in the liquid. So if I put this under pressure and I'm pushing really hard, then I'm going to push these molecules into the liquid, right? So when I open a Coke can, I release that pressure. Then these molecules that were dissolved in the water are going to come up. That's why if you leave that top off for very long, your beverage is going to go flat, because the gas, the CO2, which is in here, is going to escape up through that open top. Solubility is also an important part in industry and other things. Even like when you're giving somebody injections, you want to make sure that they are compatible or soluble with each other. Not all ionic compounds are soluble, and there's some basic rules about this. Most everything is soluble if it has ammonia, lithium, sodium, potassium, nitrate, or acetate. Okay, a chloride, bromide, or iodide salt, or a sulfate. Most all of those are going to be soluble. But carbonates, sulfides, phosphates, and hydroxides are insoluble unless they are combined with one of those that I just mentioned over here. Heavy metals such as silver, lead, and mercury are not soluble. And barium, lead, calcium, and strontium are also not soluble. So if you mix any of those with a sulfate, even though most sulfates are, they're not going to be. And chloride, bromide, or iodide salts of silver, lead, and mercury are also not. What does that mean? Well, if they're soluble, when you dissolve them, you're not going to be able to see any difference. If they're insoluble and you put two different things together, what will happen is you'll get solids forming in the bottom. Okay? So if you mix aqueous solutions, and they can both be just as clear as they can be, but if they're not soluble with each other and you pour them together, they will form an insoluble salt or a solid in the bottom of that container. Barium sulfate is an insoluble salt that is used if you're going to do some lower bowel work usually. And so you might have heard this called a barium enema, and you give this to someone so that when they it will combine and with fecal matter and things like that, and it'll actually show you where obstructions are. And so it's used in X-ray to enhance those. So we can use solubility to our advantage if we know what we're doing. If you're going to be, what you'll have to do with this as far as testing purposes is to figure out, is something going to be soluble or not. Okay, so if, like for example, a sulfide is usually insoluble, but if it's combined with a group 1, it is soluble. Calcium nitrate is soluble because it's with a nitrate salt. Lead chloride is insoluble because lead is going to make that chloride insoluble. So you see how this works? So that that previous table that we were talking about earlier has got some of these rules that you can go by. So if you look at these in this learning check, this is what I'm talking about when I say that they, and we call this precipitation, just like, you know, we call that when it rains. So like rain falls out of the sky. the solids precipitate out of solution. So when you're looking at these, what is the compound that's actually making this insoluble? Well, we know sulfide, right? Iron sulfide. So most sulfides are going to make precipitates when you put them in there. What about lead and I2? Lead. Okay. And what about NiOH? The hydroxide. So that's what's actually making those insoluble and come out of solution like that. That's all there is too about solubility, how you can use some things that will dissolve, some things won't, and how you can use those solubility rules to actually predict what is going to happen in a particular chemical reaction. Because if you know the solubility, you know if it's going to be staying in solution, or if it's going to precipitate and form a solid at the end of that reaction. So this is the end of 7.3, and I will see you back for 7.4.